Welcome back. It's just some clarification on the previous video where I was asking ChatGPT some questions like a first year diploma or a Bachelor of Engineering type things. This, of course, question here wouldn't be like in first year. I did point that out. This would be maybe depending second, third year, something like that. If you were, I mean, of course, everything's digital now, so you might not even bother with a circuit like this, but it is important to know about it at least. You know, if you're an electronics engineer, how would you analyze this? And this is what I expected ChatGPT to do, because I mean, after all, ChatGPT is not like a normal student. It's got the entire history of the internet on it. It's got a brain as big as a planet, so to speak. So how would you work out the transfer function of this? Which is what I asked it, and I got it wrong. Well, what you do is you use the so-called impedance method, where you treat it like an inverting amplifier, because it, you know, if you all of this is one big impedance, and all of this guy here is also impedance, was just a resistor. I know you can write these as, put these as a box, rectangular box instead. That's a standard, but you know, whatever takes your fancy, it doesn't matter here. We know it's a resistor and a capacitor. So we've got a resistor and capacitor in series, which we write R1 plus 1 upon SC in parallel with R2. So it's R2 in parallel with R1 plus 1 over SC, and that's this whole impedance. So therefore the transfer function V out over V in is just that whole thing, once we've worked it out, divided by R3, and there's a minus sign because it inverts. But don't let the minus sign confuse us. And kind of ignore it as long as we know it's in there, you know, it's and are aware of it. So R2 in parallel with some impedance here, R1 plus 1 upon SC, that's like two resistors in parallel, even though they're generally impedances. So we just do the product over the sum. It's the easiest way. So the product is R2 times this, R1 plus 1 upon SC, over the sum, R1 plus R2 plus 1 upon SC, and multiply. This is where a lot of students used to have difficulty. Multiply the numerator and the denominator by SC, and that this disappears, and you get 1 plus SCR1 on the top, the numerator, and then on the denominator 1 plus SC in brackets R1 plus R2. So that's that whole impedance written in terms of S. And remember, S is equal to j omega. So where omega is the frequency, so at low frequencies, DC, in other words, it's just a resistor, which is what you'd expect, because when DC comes in here, that capacitor is open circuit, and you just get R2. At high frequencies, however, that becomes like a short circuit, and you get two resistors in parallel. And to see that, you need to put S to infinity, but obviously you can't put S to infinity in there because the whole thing becomes infinity over infinity. So you need to divide by S first, and you get R2 times 1 upon S plus this guy, SCR1, over 1 upon S plus CR1 plus R2. And the whole thing becomes R1 over R1, sorry, R2 R1 over R1 plus R2, the product over the sum, which you can do. Anyway, once you've got that impedance, you just need to divide by R3. So I say I've just noticed a mistake. I've called it R1 here, so this should be R1, R3, because I forgot I've got an R1 there already. So I'll put that as R3. Oh, this is math type for you. Changes its size. So it's minus, divide by R3, and it's all this divided by R3. So it's minus R2 over R3 times this thing here. So if you label K is equal to R2 upon R3, that's the DC gain. And the reason it's the DC gain, that resistor over that guy, is because when S is 0, in other words, omega is 0, frequency is 0, you just get 1 over 1 times R2 over R3. So that's the DC gain, and minus sign didn't concern us too much. And I just relabel things. SCR1 is T1, and T2 is CR1 plus R2. And that's our transfer function, which ChatGPT didn't give us that. It gave us something like the denominator, but I think even that was wrong. I think it gave us CR1 for that time constant. And remember, it was saying it was a differentiator or something. It's nothing to do with differentiation. If you plot the frequency response, notice the T1 must be less than T2 here, because it's CR1 plus R2, that's bigger. The CR1 has got to be less than T2. So when you write 1 plus ST1 over ST2, it means that the pole, this guy here, 1 plus ST2 in the denominator, is at a lower, that's a lower frequency. Because it's T2 is bigger, it means that 1 upon T2, which is the cutoff frequency when you're doing an asymptotic Bode plot, is smaller than 1 upon T1. Should write 1 upon T2 is less than 1 upon T1, okay, as well. But you've got the DC gain, so it's 20 log to the base 10 of K, where K is R2 over R3, not R1 as I had originally. And then it goes down, it's a slope, because it's first order, down minus 20 dB per decade, until it hits this 0 here, 1 upon S equals minus 1 upon T1, or in other words, that frequency of 1 upon CR1 plus R2, or 1 upon T2. It's flat, and then minus 20 dB per decade, and then flat again. So if you didn't have this bit in here, it would be like a low-pass filter. That's simple. And of course that can be done, well, actually can't be done that easily there. You normally put the resistor in parallel, not in series, for a low-pass filter, because it's the way you're kind of stuck with something like this. And notice again, when at high frequencies, this thing becomes R2 in parallel with R1, and that's why it goes flat again, because it goes at a constant gain at high frequencies, and at DC it's a constant gain of K. So that's what it should be, and that's what the transfer function is here. K 1 plus ST1 over 1 plus ST2. If you're interested in what we use such a circuit for, probably a lot of things, but in control, which was my area, it was used rather as a phase lag compensator. If you draw the phase, which I haven't got in here, it starts at 0, and then it goes down to some negative value, which I could talk about, I'm not going to, and then it goes back up again, back to 0. So it just dips down negative and back up again. And a negative phase isn't really a good thing at all in a control system. So you might, because it reduces phase margin. So you can't use it anywhere near the unity gain frequency of a control system, open loop control system, because it would destabilize it. Instead, we actually use the opposite of this, which is called a phase lead, and it's the upside down version of this. It's a bit like 1 plus ST2 over 1 plus ST1, and when that happens, it goes along up at plus 20 dB per decade and then flat again. But this is used not at the unity gain frequency, but at low frequencies in a frequency response in a Bode plot of a control system. And what it does is it increases the gain at low frequencies. It's like an approximate integrator, because an integrator is minus 20 dB per decade. So a pure integrator would just be integrating from DC up to daylight. It would just keep going all the way down, minus 20 dB per decade, and have infinite gain at DC. But this has got finite gain at DC, so it means it's not so good for steady state error and so on. It does improve the steady state error, but not as much as a pure integrator would. So you might think again, why not just use a pure integrator? And yes, we would if we could get a hold of, get away with it. Sometimes you can't put in pure integrators and circuits, and so you're sort of stuck with this kind of phase lag thing. In phase lock loops, sometimes they have lag lead passive networks. This is the lag part. There is a bit of a confusion. Some people call this lag lead because this is the lag part is the pole, and then this is a lead. But we normally call it a phase lag in control systems. And a lag lead is a combination of this circuit with another circuit, which is the upside down version. As I say, what happens is you take all of this and you put it in here. You swap R3 with all of this, and that becomes the phase lead or a phase advance. But increasingly, of course, we're not using analog circuitry anymore, to my knowledge anyway. We can do all this in Z transforms and difference equations and so on. But it's still good to know the theory of things like this, because it comes in again when you're doing filters and the like. This will filter some signal at only at minus 20 dB per decade, but then it will stop filtering at that frequency, this frequency here, this high frequency. Okay. Anyway, so that's the analysis of it. And as I say, if you've got a brain as big as a planet with all that knowledge, like ChatGPT, you'd think it might have seen it, but because it's a less common circuit that you see, when they show op amps circuits, they show the usual ones on the internet where it gets all its info from. In books, you'd come across this, but maybe it hasn't got access to all the literature in the books and things because it's sort of sealed off, password protected and so on, behind the paywalls, and maybe that's why it didn't do it. But nevertheless, it should be able to work it out for itself if it knew a basic principle that for this kind of simple circuit, where you feed back into the summing junction here, that the voltage gain is this whole thing here divided by this thing here, and it doesn't matter what you put in there and what you put in there, you can work out that transfer function. So you could put a series capacitor in there, for example, work it out again and work out how it changes and plot the frequency response. This is the asymptotic frequency response, of course, not the exact one. The exact one's got a curve there at the cutoff frequency, at the lower cutoff and the higher cutoff. And I've missed the phase out deliberately because I don't want to make it too complicated. It didn't get that right. It was quite well off the mark, but nevertheless, just in case somebody wanted to know what it was all about, that's what it should be. Thank you very much.